Hi and welcome to Maths class. Today we're looking at logarithms. We're going to learn what they are and we're going to learn specifically to be able to rewrite exponential equations in log form because they are equivalent expressions. Then we'll learn to look at evaluating logarithm expressions when we're not using a calculator. We're going to look at our laws of logarithms and then we're going to use those laws to solve some equations and simplify some expressions. So let's get started. All right, so what we've got here are some definitions initially. So if I write a to the power of n equals b, then that is the equivalent of log base a of b equals n. And in this case, we're assuming that a is a positive real number, except for 1. We're not including 1 because 1 to the power of n is still just always going to be 1. So it's a trivial example. So on the left, when I look at a to the power of n, a is my base and n is my power and b is the answer. When I'm in the logarithm, the language I use, a is still my base, but b is now called the argument of the logarithm, and now n is the answer. So it's important to be able to recognize that the answer in the log equation is equal to the power in the exponential equation. So the n in the exponential equation is the power of a, and it's the answer to the log equation, which basically means that when I write log base a of b, what it's really asking me is a to the power of what is going to give me b. So in this next example, 3 to the power of 4 equals 81. When I've got log base 3 of 84, that's asking me 3 to the power of what is going to give me 81, and the answer is 4. So these two functions are inverses of each other because we are swapping x and y when we write them. If I've got y equals a to the power of x and I rewrite that as a logarithmic equation, I get log base a of y equals x. I'm now going to swap x and y in order to find the inverse, which will give me log base a of x equals y. So it therefore follows that if these are inverses of each other, then remember that an inverse undoes the equation. For example, the inverse of x squared is the square root of x. So if I start with 5 and I square it, I get 25, then I square root it, I'm back to 5. So if I do an inverse of a function and the function, I should get back to x. So a to the power of log base a of x equals x. That's when the log base a is the inside function, and when the log is the outside function, I get log base a of x. That also equals x. Now I'm just going to show you something here using Desmos. That's the one. Okay, so what you've got there, what you can see, the blue graph there is y equals a to the x, and the red graph is log base a of x. And the dotted line there is just the line of y equals x, because when I sketch the two, obviously we know that when an inverse is sketched on the same set of axes as the original function, then there is a reflection through the line y equals x. Now these two particularly don't cross this line, they never equal each other, but that's because I've used a value of a that is greater than 1. In fact, these graphs are base e. But if I show you two different graphs, there's y equals 1/2 to the power of x, and there is y equals log base of 1/2 of x, then you can see these are also reflected across the y equals x line, and they do also meet on that line. There is an intersection point between them. But you can see that the logarithm has a vertical asymptote, and the original exponential function has a horizontal asymptote because x and y are swapped, so the asymptotes also get swapped. All right, so that's just a quick look at that. Let's go back to our notes. All right. it's important also to note that the argument of a logarithm must always be positive. That is, b is always greater than 0. And remember, if you go back to the top there, we are assuming that a is a positive number. So if I raise a to a power n, then it's always still going to equal a positive number. So for that reason, log with a base of a positive number has to have a positive argument. And the argument, remember, is the number inside the logarithm. So that's what's going on there. Okay. Here are a couple of specific examples of logarithms. You've got the natural logarithm base e, and that's the one that we will deal with the most. So in this case, if f of x equals e to the power of x, then the inverse function of f is log base e of x. Please note that your calculator or some computers will use the notation ln of x, but in our writing we always use log base e of x because that's the mathematical way to write it. Ln is just a shortcut when we're using base e. The second really common example we have there is the common logarithm, which is base 10. It's called the common logarithm. It was really used a lot before there were calculators. So we used to have log tables that we could look up, but in this case we don't need to look up any log tables because these are pretty easy to do. If you remember that the logarithm, log base 10 of 10 means 10 to the power of what is going to give me 10? Well, the answer is 1. Oops. And for the second one, 10 to the power of what is going to give me 100? The answer is 2. And 10 to the power of what is going to give me 1,000? The answer is 3. Here, 10 to the power of what gives me 0.1, remembering that 0.1 is 1/10, so that's 1 over 10, so that's -1, power of -1. Similarly here, log base 10 of 0.01 is asking me 10 to the power of what gives me 1 over 100, 0.01, and the answer is power of -2, and this one the answer is power of -3. That's a 3. Okay, so now what we're going to do is we're going to learn about the laws of logarithms. So we're looking at laws of logarithms, and I'm just going to start. I'm going to show you the first law of logarithms and where it comes from. I'm not going to show you the derivation of the others, but I'll just show you this one. So we'll start with, we've got let m equal a to the x, and then we're going to let n equal a to the y. Right? And this is what I'm going to use to show you where my laws of logs come from. And they are very closely connected to the index laws. Now, if I rewrite this first expression in logarithmic form, remember that a is still my base, but now the power becomes my answer. So this is log base a of m equals x. And over here, this one will be log base a of n equals y. Okay. Now what I'm going to do is I'm going to go back to my original expressions and I'm going to multiply them together. I know that m times n is going to give me a to the power of x times a to the power of y. And using my index laws, I know that these powers are going to be added together. So that gives me a to the power of x plus y. So that means that m times n equals a to the power of x plus y. So if I rewrite that now as a logarithm, that tells me that log base a, log base a of mn is going to be equal to x plus, what is going on? X plus y. So that means that a to the power of a to the power of what gives me mn? The answer is x plus y. But I've got another expression, an alternative expression for x plus y using this and this. If I add those together, I'm going to make that log base a of m plus log base a of n. And that is my first laws law of logarithms. All right, that's my first law. Right there. What it's saying is, and this can work in both directions, I can go that way or I can go that way. If I've got log base a of two things multiplied together, I can expand that to be log base a of the first thing plus log base a of the second thing. Or I can bring these together. If I've got the same base, two logarithms with the same base added together, then I can simplify it to multiply there. So let's have a look at our other laws of logarithms. That's my first law that we've just looked at there. The second law is the same, but it's using division instead of multiplication, and what I have in the middle there is a subtraction instead of an addition. Now, this third law is sort of an extension of the first law. If I've got m to the power of p, that's m times m times m times m times m, p times. Log base a of m times p is the same as log base a of m plus log base a of m plus log base a of m, p times. So this is a special case of the first law, but it's really useful. It means that if I've got a power inside my logarithm argument, then I can bring that power out the front as a constant to multiply, and vice versa. All right, and you'll see me use that in a little while. The fourth law is related to the fact that m to the power of -1 is the same as 1 on m. So when I've got to the power of -1, that becomes a subtraction of log base a of m, or we can see that as the -1 being multiplied out the front. And then law 5 are two standard logarithms. A to the power of what gives me an answer of 0? The answer is always, gives me an answer of 1, that's 0. Anything to the power of 0 will give me 1. And a to the power of what gives me a? The answer is always 1. So logarithm base a, where the argument is the same as the base, always gives me 1. So let's do a few examples. First of all here, I've got this to simplify. Now, the first thing that I see here is I've got log base 10 and log base 10. So the bases are the same, but I can't use my second law yet because I've got this 3 in front. So what I'm going to do is I'm going to rewrite this. I'm going to keep that log base 10 of x minus, and I'm going to bring that 3. I'm using the third log law here. I'm going to make that into log base 10 of x plus 1 cubed. And that's by going this way using my log law 3. Now these are subtracted, which means I can go this way using my log law 2, and I can collect those together. So I keep the same base, but I'm now going to have x as my numerator and x plus 3 cubed as my denominator. And that's as simplified as that can get. Notice that that was the command here to simplify. So that's what I've done. All right, we're going to look at another example. What I'm going to suggest is that you try this one. Hit pause now, try it, and then watch me do it and see how you went. So I'm going to simplify log base 5 of 81 over log base 5 of 3. The first thing I'm noticing here is that 81 can be rewritten with a base of 3 as an exponential. So I'm going to do that. Log base 5, instead of 81, I'm going to write that as 3 to the power of 4 because that does equal 81. Keep my denominator for now. Log base 5 of 3. Okay. Now I'm going to use my log law 3, but this time I'm moving this way. I'm going to take that power there and I'm going to bring it out the front as a constant that's multiplied. So I'm going to take this power of 4 and bring it out the front. So that's 4 log base 5 of 3 over log base 5 of 3. Now, what we have to remember here is that a logarithm is a number just like any number. If this was 4 times 2 over 2, you would know what to do. If it was 4 times pi over pi, you would know what to do. It's the same thing. This is 4 times the number that is log base 5 of 3 over the same number, log base 5 of 3. So we cancel them out and we're left with 4. And that's it for that one. All right, let's look at the next one. Now we're solving equations. We're no longer simplifying. We need to find x. I'm going to suggest you pause and do it yourself. This one is very straightforward. We're using the fact that this can be rewritten as an exponential. Okay, so log base 10 of x, remember, is saying 10 to the power of what is going to give me x. All right, now this can be rewritten as, remember, 10 is my base, and the answer over here is always my power, and that's going to be equal to x. So x in this case is 10,000. Now, let's check it. Log base 10 of 10,000 means 10 to the power of 4, to the power of what gives me 10,000, and the answer indeed is 4. Okay, just 2 more examples. Here's my 4th example. Again, pause it and try it yourself. So I've got log base 2 of 3x plus 1 equals 4. Now I'm going to rewrite this again. So just to help you, over here I'm going to write a to the power of m equals n, and now I'm going to write log base of a of n equals m. This is a rewriting, okay? So my base is always the base here. They stay the same. The power in the exponential becomes the answer in the logarithm, and the answer in the exponential becomes the argument in the logarithm. So let's do this one using that to help us. The argument in the logarithm is going to be the answer, so I can write it on one side of the equation. And on the other side of the equation, I'm going to have the base, which is 2, raised to the power of 4. Okay, so I've rewritten it just the other way around from this. Right? I wrote n equals a to the m instead of a to the m equals n. It's the same. All right, so this gives me 2 to the power of 4. That's 16. So 3x plus 1 equals 16. Now it's linear. We can all solve this. 3x equals 15, x equals 5. And we're done. Okay, one more to go. This one's a little bit trickier, although not too much. Have a go at it. See if you can figure out how we can solve this one. Okay, I'm going to do it. I'm going to start by using my second log law again, and I'm going this way. I'm going to collect these together, because remember that when I'm trying to solve an equation, I need to get x on one side of the equation by itself. The best way I can do that is to bring them together in the argument of this logarithm first. So I'm going to make this log base 2 of x plus 3 over x minus 2. And that still equals 3. I haven't changed that. If I now convert this to an exponential, then that's going to help me solve this. So on the left-hand side, I'm going to have x plus 3 over x minus 2, and that will equal, the base is 2, and the power is the answer on the right, which is 3. So that is 8 on the right-hand side, and on the left-hand side, x plus 3 over x minus 2. Now you should know what to do. I'm going to multiply across by this denominator. X plus 3 equals 8 times x minus 2. Nearly done, which gives me 8x minus 16. So I'll just bring the minus 16 over to the left to be 19 equals 8x minus x equals 7x. I'm running out of space. X is 19 over 7. Okay, so just going back to my first slide quickly. Right, we learnt to rewrite exponentials in log form and vice versa. We practice evaluating some expressions without a calculator. Oh, we didn't really practice that. Oh yeah, we did that with the base 10, we did that. We did some logarithmic functions as an inverse. We looked at that graph. And then we solved some equations using laws of logs. Okay, so that's the end of logarithms.